for you. Professor Patricio Mendez and his presentation, The Science of Welding. Professor Mendez is Industry Chair in Welding and Director of Canadian Centre for Welding and joining at the University of Alberta. Dr. Mendez holds a PhD and Master of Science degree in Materials Engineering from MIT and a Mechanical Engineering degree from the University of Buenos Aires. His research, as far as I understand it anyway, centers around the idea that welding is very accessible, very salient force in our economy especially, but there's very deep science, of course, that informs it, especially in dynamic environments such as over here. Take it away, Professor Mendez. Thank you very much.
Well, thank you for being here, having our first sunny weekend of the year, and you're here in a loft room with me. I appreciate that. So it's good too, because I feel welding, I feel a passion for it, and many of the guys in our lab do too. And let's see how much of this I can convey across. So this is a photo from our lab here, and I'm going to tell you a little bit more about me and about our lab, and of course about welding. But before I get serious, let me tell you something. Bad welds are bad, right? This is what happens when you don't weld right. This is a World War II example. These are the Liberty ships. Well, I don't know if you know, but about as many ships sank out of structural failure than as by torpedoes, right? So that's one thing. Now, conversely, still in World War II, this is what welding is good. The Graf Spee, I don't know if you know, but it was what is called a pocket battle cruiser. And after the Versailles Treaty, after World War I, the Germans could make big ships. And before they decided to do whatever they wanted, they decided to, still within the constrictions of the Versailles Treaty, to make ships that were as powerful as the most powerful ships out there. And what they did is replace rivets by welding, and then they could be light, as they had agreed, but still powerful as any other ship. So the British fleet had to divert a significant part of it to chase after this one, and eventually they got in the South Atlantic. So that tells you what bad welds are and what good welds are. And beyond World War II, welding happened to still be relevant. The Apollo mission almost failed to put a man on the moon before the decade was out. And there were two things that could have made it fail. One was the problem with the insulation in the second stage, and the other was the problem with welding in the second stage, because they were welding aluminum for which they didn't have enough experience for the tolerances they needed. So they ended up welding in something close to what is a clean room. But it took them very long to figure out. So welding, again, like what is good is really good, what is bad, it can have very bad problems. Today, like rockets, welding is essential part of making rockets. But the Airbus A2000, this is an interesting example. It's luckily a more peaceful example than the Graf Spee, but it's the same thing. In the A380, one of the reasons they could make it this big is because they replaced rivets by welds in many parts of the plane. And for that reason, the plane is lighter, and they can make it this big and still fly. This is interesting what mostly the French did. They stole the welding scientists from the Soviet Union after it collapsed. So it has lots of laser welds in there. If you think that welding is relevant here in the province, well, I can tell you it's very relevant. And I don't know how many people really care about welding, but I can tell you this. Every one of us here cares about the oil. Because in the end, probably almost all our salaries come from the oil. And no welding, no oil. So, and then here, if you like arts, the big sculptors, big bronze sculptures, you believe they're a single piece, but they are not. They cast them in chunks. You see these little squares here? And then they have to be welded. So, welding is so relevant. Now, can I tell you a little bit about the relevance of welding? I'll tell you a little bit about myself. So, the charming accent is from Argentina. I'm a mechanical engineer. I worked there in Argentina in research for a while, both in wind turbines. Before I saw light and I moved to oil and gas, I guess. And I worked at a company called Tenaris. Actually, Tenaris is an Argentinian company with branches all over the world. Even in Nixville, we have a manufacturing site for Tenaris. From there, I went to Boston. I went to MIT. I got my master's, my PhD there. I partied all right, but wasn't a big problem. I had a startup there, always in metals-related technologies, and I was a consultant for a while. But being a professor is a lot more interesting, and I made the jump from Boston to Colorado, and in Colorado I joined the Welding Research Center, and that's how things started to take this serious color of welding for me. I'm interested. I used to run a foundry too. This is our actual foundry. It was the largest operating foundry of any university in the US or in Canada. And this is Mount Davis. It's the highest paid road in North America. And then, after spending 4.5 years in Denver, I got poached. And I came to Edmonton. Now, that's me on my bike again, but it's a different picture. My mandate here was to start what we call the Canadian Center for Welding and Joining. That is a center with the function of bringing the deep science and the deep engineering into making new technologies for welding. Here in the province, we have needs. Because of the cold, because of the oil sands, we have needs for welding that you cannot buy off the shelf. We're not a big enough market for like the worldwide companies. So what do? So we're forced, and it's beautiful to be forced this way. We're forced to come up with our own technologies. And I think we're doing an okay job at that. I'll share with you a little bit of what we have going on. So this is a photo of our lab members. And you get to see, this is quite big. This Canadian Center for Welding and Joining is a very interesting thing because we're in a university, we're an academic entity, we're a research entity. I need to publish like everybody else. I need to talk to colleagues, solve differential equations, which I actually love. But the impetus for this operation at the university didn't come from the university. Actually, the university had a program when the professor retired, the program disappeared. And nobody really mourned it much until people in industry here in the province, they couldn't get an engineer that had a sense of what welding was. So that's a problem, right? Because everything was welded. Pretty much everything you do here in the province, when it comes to the materials for the manufacturing or the operation, goes through welding. So the industry came to the university and said, we need to have something more welding. And the thing we have, who's a very smart guy, said, of course, we can make that happen, but it's going to cost you. And somehow he taught the industry to put $3.5 million of their hard-earned money into creating a program in welding. Right? They created a WELCO industry chair in welding and joining. It's an endowed chair. This is the president of the leading company, WELCO. And not too long ago, we opened up our lab that was in, look, today's May 5th, right? On May 5th, exactly 3 years ago. So we're celebrating our 3rd anniversary of the open lab. And we also, in addition of things, teaching welding at the engineering level, we do industrial outreach. And the industry is expanding quite a bit. To put it in context, $3.5 million, our lab right now is a facility of $3 million. And that's very sizable, both in space and the capabilities we have, which means it's a lot of fun to be there. These are the companies involved. You're likely familiar with many of them, like Syncro and Suncor, I'm sure. Those of you who know anything about welding already, Lincoln and Miller, Coke and Pepsi, the two leading companies, competing very closely. And we have a long list of other companies outside the endowment who wanted to participate in this activity. It's a little bit of the Stone Soup story, right? Like you start with with water and stones, but if people help you with a little bit of something, more people want to help you, and in the end you have a real suit. And here we have an amazing outpour of goodwill and help from industry and the university and the government. We also host open labs. These are photos from the open labs, and the ones teaching in front of the boards are our own students. And we have robots. It's fun. And it's fun not only doing the research, but also communicating it. That's one of the reasons we signed up willingly to be here with you today. Sunny day, and thanks again for being here. You don't see it, but I get to see all the sun pour through the doors. So, okay, welding and engineering. So I want to tell you the first thing that I think would be useful. Do we weld enough, right? Do I train welders? And the answer is no. I don't train welders. Actually, I don't train, I educate. But the important thing here is welders are like virtuosi, like Paganini. They can use their hands and have this skill that is nearly magical. Right? No, we're here with the skeptics. No magic. Okay, but but whatever it is, it's very hard to explain, right? And they can do these amazing things. Now, the tools they use, like Paganini would use a violin, which actually was made by Stradivari, right? Who makes those tools? The one who makes those tools needs to have a whole different set of skills and insight. Right? Maybe they know a little bit how to play, right? But the real talent is in putting these machines that would be so amazing together. So we are like Stradivari. Here's a photo of our lab, looking at our equipment, right? So that's the main difference between welders and the engineers. We're here. Joining. What is welding? Let's start. Welding is putting two things, right? Put two things together. And I think the best definition is from an institute in England called the Welding Institute. And they went for Latin. Et duobus unum, right? That would translate loosely from two to make one. That's the best definition. You have two things, and if you join them right, they became one. That's the basic I hope for. It never happens, by the way. So, welding is part of the manufacturing process. You do it when you already have much value added into your parts. You don't weld two chunks of iron ore. No, you weld two plates of carefully alloyed steel that maybe was heat treated, maybe was machined. Lots of value added. So when you screw a weld, you're screwing the work of everybody before you. And there's a whole lot of love to be lost when you do that. So what is welding? Right? In welding, we do melt the plate. There are subtleties, right? Like, do I melt the plate? Don't I melt the plate? And I'll tell you a little bit about those in the next slide. Now, do I melt the plate with a big spark, or with a laser, or with a flame? Whatever you did, if you melted the plate, that's welding, right? And the important thing of welding is that after you melted it, the interface that you had that separated the two parts, right? Right now, there is an interface between this table and this cabinet here, right? And I can put it apart. But in welding, what we do is we do away with all this interface, right? By melting it. And then when it goes solid, there's no interface anymore. The atoms, right? The atomic bonding level give continuity all through the joint, right? So that's the important thing. It's different than bolting. Right? In bolting, I will keep these two together as long as I have my bolts, but the interfaces are still there. So you might or might not add new material. That's secondary. So, and of course, if you were to look at the material in microscope, materials look very patterned, much like the tiles here on the floor. And when you do all this heat, this pattern gets very altered, and that's how. If you know what to do about it, you can become a consultant and make a lot of money. And come to our level, I'll tell you how. So, dispelling a few either misconceptions or addressing some questions before you ask me. Soldering, right? Here electronics. This is not welding. Funny, in Spanish we use the word welding for all, but in English we separate. So this electronic thing is different. We melt this solder. So we do melt the solder, but we don't melt the plate. We don't melt the microprocessor there, or you shouldn't, right? I hear the most important one. I hope nobody here works with JB Weld, but let me get this straight. JB Weld is not welding. That's an epoxy. And despite that they call these, the black one, they call it the steel. No, that's not steel. That's a polymer. Which polymers are beautiful and they do many good things for you. But welding is welding and metal is metal, and there's a reason why that they use that. Right? So, now that we are clear on some things, and tell you what we do here in Alberta that is interesting. And I'm going to drop these words just in case they resonate with some of you. So, sailing, welding, so many people, especially those who might have seen old movies, you think that most welding is done with a flame torch. Well, true, but that hasn't been used in so long that they don't even teach it at places like NAIT now. You can use lasers, you can use like a little stick, right? Like the guy with the little stick welding? Okay, they call it stick. And bees or MIG or TIG, flux core, glass mark, except the first one and except the last one, right? All these ones in the middle we call electric welding. And if you're a welder and you care about this, there are lots of subtleties to mind. But overall, the science has many similarities. And that's the science I want to talk about. The science of electric welding. So let's take a fantastic voyage into the weld, right? So just to start, you saw, especially if you've been around campus, a welder, a beam, right? Like you see this bright spark. Here we have our Joe welding a beam in a building construction. So let's go closer. Okay, here we have Joe with a smile, and here's his weld, right? I like to see the sparks. And pretty much everybody who works with welding, they love these pictures. Right? Oh, the sparks, look at all that. Well, this is so old school because the message you get from here is the sparks. Let's go one more level in, and to the level in which, for welders, it becomes difficult to discriminate. So now, okay, let me go back. So you see the spark, right? And here you have the weld. Now let's look at the weld. So here, all this is the weld. Right, and if you filter the light properly, you can see things a little bit more clearly. That's why the welders have these tinted glass. So here you have molten metal. Here you have this bright light, which we call an arc, and which is plasma. And here you have the electrode. There are so many types of electrodes. All these long list of different welding processes I mentioned 2 slides ago, they all depend on, do I make my electrode? I don't make my electrode. Or do I make my electrode and then I have to chip off some slag? Or don't I? So those things, within the same science, those subtleties matter a lot. Again, you get to see. Right, so now we are deep into the weld itself. And you realize that, well, this width might be about 5 millimeters, right? There's a whole world going on in there. Right here, you can see something that is amazing. Most disciplines of either science or engineering work in what is called an equilibrium, in which if something is hot, it's hot, if it's cold, it's cold. But in a weld, you have to be hot somewhere, and you have to be cold somewhere. Because if you're not hot, you just melt the metal, and then it doesn't melt. But if you're too hot, then you melt everything else, right? And then you have another problem. So in welding, by definition, yet with no other way around, you have to be out of equilibrium. And it's amazing how our Paganini's can make these amazing welds without realizing they're doing something so complex that many people are not even educated to think about this lack of equilibrium. You cannot go too fast, you cannot go too slow, and somebody figure it out. Alright, so this is now taken from our lab. This is a photo of a weld process. They call it gas tungsten arc welding. It's one of the welds in which you don't melt your electrode. So this thing that looks like a pencil, that's the electrode. And it's made out of tungsten. Tungsten has 2 things that are important. It's a very high melting temperature, right? That's why old school incandescent bulbs had a tungsten filament. But also, it's easy for tungsten to give electrons away when it's hot. That's called fermionic. right? And that's why they would use tungsten in the old tubes, in the old electronics, right, with the vacuum tubes, or in a CRT you have a tungsten tube. So here you have our electrode, and although this image might not look all too clear to you, this is about the best you can do for looking at welding seriously. This diamond is very bright. What you see here is the plate. Here's you see traces of what the weld puddle is. Here we have current flowing. And here we have this big bright thing. This is the plasma, right? And current is flowing. The electrode is not touching the plate. You have a gap in there. So one of the scientific questions I wanted to address here, and I'm oversimplifying things quite a bit, but isn't that amazing that I have a gap and I still have current flowing through it? Right? I mean, as far as I knew, if you wanted electricity to go, the two cables have to touch. Right? Well, they don't. So how does it go through the gap? And it's because it's a plasma. And in plasma you have the electrons, right? Like we have our atoms with the nucleus and the electrons. The outer electrons in the outer orbits, when things are hot enough, they are loose, and then they become a conductor, somewhat similar to metals, right? Of course, it's a different way of conductivity, but these loose electrons are charge carriers, and they can conduct 200 amps. 200 amps is a lot, by the way, eh? So it's you don't want 200 amps going through you, that's for sure. So, of course, in the gap, it's not a vacuum, it's a gas. Typically, the gas is an inert gas, argon, typically, because inert gases don't react, so you would not oxidize your material. You would introduce alloying elements, you would not take alloying elements out. You can also use helium if you can afford it, right? So, that's how electricity gets carried, right? Things are hot, electrons are loose, and then they carry electricity. But the other question is, something I said in the abstract. How hot are these electrons? Well, the ultimate truth is very hot. Very hot. Look, the surface of the sun is more or less 6,000 Kelvin. Right? And it's a plasma. The bright light of the sun is essentially a welding arc, a weak welding arc. Because what we have here is 20,000 Kelvin. And if you can see this in many ways, people can measure it by using spectroscopy, which we have a spectrometer in our lab. Or you can do numerical modeling. This is the results from a numerical model we did when I was still in Boston. And this red part here, that's 20,000 Kelvin dead on. That's very hot. That's very hot. That's lots of ionization there. And one of the reasons it's so hot is because at atmospheric pressure, the ions and the electrons are close. So for the electrons to move, everything has to shake. Right? For example, if you look at the ceiling, you see the fluorescent tubes, right? There's a plasma tube. Now, you bet any money that that's not 20,000 Kelvin. You can even touch it. And the difference is that plasma is at very low pressures. So at low pressure, the electrons and the ions are separate. So the electrons can move without causing all this heating in the ions. We, in the past, when I was still in Colorado, we wanted to do an experiment. What it would be to weld on Mars. Mars has a CO2 atmosphere that is used as a shielding gas in many cases. So we said, all right, might as well try to weld like we're in Mars. When we turned on the welding machine, everything was glowing because at the low temperature of Mars, that is 10% of an atmosphere, or 1%, I don't remember now, but it's, either of those would be real bad, like everything ionizes. Right, that was an interesting experience. But on the Earth, things get hot. So, as I was mentioning, it's so hot because electrons move and heat everything. That's why you need a mask, you need protection equipment. There's lots of ultraviolet. Lots of ultraviolet. Right? The amount of energy in a weld is more or less the same as connecting an iron. And you never think you're welding your shirts when you iron them. But if you were to concentrate all the power of the iron in a 300 times smaller area, probably you would have some ventilation. So the other interesting thing is that electricity causes motion, and we know this because that's what happens in electric motors, right? Electricity can do pretty interesting things for you. And so look at this. If you model the electromagnetic fields running well, what you would see is that where the arc is narrow, you have like tight magnetic fields. When the arc is broad, you have broader magnetic fields. And that creates motion. I think these arrows come from the same model that I discussed before about inducing motion in the same model of the arc. Look, if tighter magnetic fields make stronger electromagnetic forces, and the top is tighter than the bottom, as you get to see with your own eyes, right? Have more pressure on top, and this pressure differential causes motion. Right? That's Bernoulli's law, for those of you who are familiar. It can be as simple as that. But the end result, by the time you do your calculations, is that the velocity of the plasma is about 300 meters per second. Now, 300 meters per second is pretty fast. Faster than this plane, for example. Right? It would be the speed of sound at room temperature. Now, when you're this hot, the speed of sound is much faster. So the plasmas in welding are typically not supersonic. But the velocity they have, this is pretty impressive. And all these can be controlled by a guy who barely finished elementary school. Right? I think you trust your life by walking next to a pressure vessel that you don't know that is an incredible pressure. The guy to study all this motion and temperatures in welding, you need to use the discipline of Magnetohydrodynamics, which is an awesome buzzword to drop at a party, right? And the guy who started this discipline is Hans Alfvén, who got, for doing this, the Nobel Prize in Physics in 1970. He was doing it for the surface of the sun, to explain some of the plasma arches on the surface of the sun. By the way, he's one of the very few, he's the only one I know, engineers who got the Nobel Prize. Okay? So, again, there's some more to welding than just being big and burly. And not only is very theoretical, because it has consequences. This fast plasma, these are products of my PhDs. I'm glad I get to use them for something again. So, these welds have all these effects that are a consequence of the fast plasma that acts more like a cutting torch instead of a welding torch. So you're going to know what you're doing. And to know it, you need a lot more than elementary or high school, or even bachelor's education. So now what about the electrode? So let's see. Here we have this tungsten arc welding that didn't melt the electrode. But sometimes if you wanted to add material, you want to melt the electrode, right? And you can melt it into many small droplets or a few big droplets. Here you have the droplets, you have current, typically you reverse the polarities, the current goes in the other direction. But you still have a plasma arc, and you still have electromagnetic fields, and you still have heating. And I want to show you what it looks like when you look at this electrode from close up, as we do. So we're right at the core of what the weld is. And let's see if I can control the lights here. Which I believe I can. Somewhere.
Wow.
Okay. Oh, I don't get it well. Okay. So look, you saw big droplets, few big droplets now, many small droplets. One was called the globular transfer, there is spray transfer. When you care about the quality of your weld, this matters a lot. Right? This is called short circuit transfer. Who knew that short circuits could be good for something, right? Well, it's in short circuits, when the electrode does touch the puddle, right, the molten metal, then you have a surge of current. Now, this is some of the work we're doing in the province, and that nobody knew before. And so this, you see, is new even for people in the field. You see this powder? This is wear-resistant powder. It's tungsten carbide. This is what some people call Vivia, right? What you use to cut glass. Okay, these powders are made of that same material. And this is for wear-resistant protection wear protection in the oil sands. So, what you see here, there's so much to talk about, right? So, let me go to. When you measure current and voltage in this video, you can do something that looks much like an EKG, because as much as your heart beats, you have also these blips in the droplets as they come in and out. There's so so much depth you can go into welding, and you can do so much math, right? So, talking about that, my last two slides. Welding is interdisciplinary. You need to know your physics, and you need to know the language of physics, which is math. And you need to know a ton of engineering, from mechanical to solid mechanics. You need to know your metallurgy, you need to know your chemistry, and that's what we're working very hard in the lab. You need to know your electricity, issues of civil engineering, and none of this would make sense if it wasn't economical. So even that you have to keep in mind, right? The current push for welding worldwide is to understand welding. Because yes, we can weld, but if you don't understand it, you use new alloys and things get tough. So this is my last slide, and that is the ultimate message is that welding is fun. And here we have our robot welding a little thing, so you get to see this is in our lab. And if you are interested in anything else about welding, we have a website with all the videos I showed you, and photos and a lot more details. So, on that note, I hope you guys have good questions. Thank you very much.
So we're actually running short on time here. You have time though for a couple questions.
I've been a blacksmith, so
Okay.
I'm a blacksmith. The forge welding, how does that differ from some of the other welding?
Okay, so the question is, there are ways of welding in which you don't melt the substrate. It's called forge welding. It's the oldest type of welding. The Egyptians used it for jewelry. And what happens in that case, if you have two pieces of metal that are very hot, and you bend them hard enough, eventually the atoms get in contact with each other and becomes a single piece. Right? There are very modern incarnations of that. And the external tank of the space shuttle was welded with a modern incarnation of forge welding. Yeah.
Do you do any friction stir welding?
Good, excellent question. That's the modern incarnation that they use in the space shuttle. And yes, we have a friction stir welding machine in the lab. Yeah. That's solid state. You don't melt anything, and you still get the atomic bonding.
What's the most interesting weld you've ever made?
Oh, the most interesting welding ever made.
No, that you have made.
That I have made. Well, first of all, the guys make the welds. I can tell you why they don't go well at times. So, interesting welds we have made. I think I did this one. You saw these photos of the welds that had all these horrible defects. The interesting thing is that nobody had an explanation for those. And as we could understand that, it was very deep to see how these plasma related to all the heat transfer. And then to see it in action, you see it with different eyes. You start loving what everybody else hates. Right? So that was very interesting.
And it seems like that would be very reproducible, strictly research, critical reliability structure. But most welding systems are people. Is it a matter of finesse of the welder or flexibility or economics?
Okay, good. So the question is, with a robot you have lots of reliability and consistency, but it's still most welds are done manually. So, and that's a big deal. Big welders and bad welders and so-so welders, they're all out there. You never know what you're going to get. So there is a push for, and there is an enormous scarcity of welders, especially quality, high-level welders. So there's a big push that nobody opposes, everybody's on board, to bring more automation into welding. Also the welding machines all use some of these science, and they have a computer inside. So as long as you put the torch in the right place, the machine for you and gives you the right voltage and current and everything else. And now, if you don't put the torch in the right place, it's still bad. We're working on that in our lab, trying to make sense of how you quantify what putting the torch in the right place is. Yeah.
Thank you very much.